We have spoken a lot about how 0 over 0 is indeterminate form, but another sort of indeterminate form is infinity over infinity. And it turns out that we can use L'Hopital's rule for this as well. So if we were looking for something like this, the limit as, let's say, x approaches infinity of e to the x over x squared, obviously we know e to the x is a whole lot more powerful than x squared when we plug in a big number. So in fact, we know this is going to be infinity. But if we pretended we didn't know, if we just knew that this is infinity over infinity, we could use L'Hopital's rule as well. The limit as x approaches infinity of, well, the derivative of e to the x is e to the x, still infinity. On the bottom, we get 2x. And in fact, since we still have infinity over infinity, let's use L'Hopital's rule again. Limit as x approaches infinity of the derivative of the top is e to the x, the derivative of the bottom is just 2. And then if we compare what's going on here as x approaches infinity, this is just infinity divided by 2. So the limit for this is infinity, as in fact we would have predicted. Let's do another one. Let's do something like this. The limit as x approaches infinity, and let's look at ln x over x. So consider, in fact, what this looks like. ln x, if you're going to compare the two, is one of those functions that rises very slowly, as opposed to x. Certainly, at this end of the graph, x is a whole lot more dominant than ln x. So I'm guessing that we're going to have a much greater number on the bottom than the top. So this, at some point, I'm thinking should be equal to 0. Let's use L'Hopital's rule, because right now we have infinity over infinity. So we have the limit as x approaches infinity. The derivative of ln x is just 1 over x. The derivative of x is just 1. So really we're just looking for the limit as x approaches infinity of 1 over x. And sure enough, that's going to be equal to 0, as we would have expected.